Thank you for the invitation. It's unfortunate that Igor isn't here, even though he's yeah. So today I'm going to talk about infinitely stable disorder systems on emergent fractal structures. Basically, I'm going to be talking about how certain classical systems react under disorder. These systems are physically motivated, but have the peculiar property that they exhibit ordering, even if I add infinite disorder into them. In fact, the disorder is going to generate an emergent fractal structure, and the ordering is going to live on the boundaries of these fractal structures. This work was done with Nick Crawford at Technion, who's in the math department, and the top two corners are the references to the paper. I want to mention that the results here are going to be mathematically rigorous, but for this talk, I will talk about the intuition behind the proof instead of all the mathematical details. But of course, if you're interested, you can always look at the papers. Okay. Oh, and I'm a postdoc at Merritt. Okay, so before I actually talk about the model that I have in mind, let me give you a quick review of classical static. So generally, you start out with a Hamiltonian that depends on the spin configuration on some lattice. You calculate the thermal average of some local order parameter at some fixed temperature T. Usually, this order parameter is your spin degree of freedom at some lattice site, say the origin 0. And if the system undergoes a phase transition, then at low temperatures, the order parameter should be non-zero, indicating a symmetry broken phase, while at high temperatures, it's 0, indicating a symmetry preserved phase. And then, of course, there's this critical transition temperature separating the two phases. Okay, so far, so good. Now, of course, in general, it's very hard to understand a stack mech model at finite temperatures. So what people usually do is to first look at the ground states. It's easier to understand and obtain, and especially if they are degenerate, then this usually implies that there is a phase transition. Okay. In this talk, I will also start out by looking at ground states to give you an intuition behind the model, but ultimately the rigorous statement is formulated within these finite temperature order parameters. Okay? Okay, so of course we have the classical Ising model as an example. You start out with this Ising model. Tau corresponds to the spin degree of freedom up or down on the lattice. And it has this Z2 symmetry, which is also shown from the two degenerate ground states, either all up or all down. Okay? Now, for a disordered model, the formulation is a little bit different, but it's pretty straightforward how you modify it. Instead of one Hamiltonian, you have a Hamiltonian for each disorder realization, where I use alpha for my disorder realization. You calculate the order parameter for each disorder realization, and then you average it over all disorders. So if the system undergoes a phase transition, then what this means is that at low temperature, the disordered average order parameter is not 0, and at high temperatures, it is 0. Now, this, of course, and then there's a critical transition temperature. Now, the important thing is that when you look at ground states for disorder systems, you have to look at the ground state for each disorder realization. And then if there are multiple degenerate ground states for each disorder realization, then, of course, there is usually a phase transition. Okay, so with that review, I'm going to start the outline of this talk. I will first start with the motivation of why I'm studying this certain class of statistical mechanics. I will introduce the explicit model, in which I will first guide you through how we find the 0 temperature ground states. If there are multiple ground states, then that means there should be a phase transition. I will then move on to the finite temperature system, and I will give you an idea of how the proof works, in which I will show that the transition temperature is independent of the disorder strength. What that means is that if I add more and more disorder, my transition temperature will not change, and that means it's infinitely stable. Finally, I will talk about 2D systems separately. The reason behind this is that in 2D systems you have the BKT phenomenon, which is basically you're replacing quasi-long-range order. You're replacing long-range order with quasi-long-range order. So 2D systems and higher dimension systems have to be treated separately. So for the majority of this talk, you should just think about 3D systems. Okay, and then I'll end with a summary of this talk. Okay, so motivation. So in general, a disorder is an undesirable trait that destroys coherence in a system. The most famous example that I know of is the Emery-Ma phenomenon. It basically says that in low dimensions, any weak amount of disorder is going to destroy your ordering in the system. For example, in 2 dimensions and below, if the system has discrete symmetry, then any arbitrarily weak disorder is going to destroy ordering. For continuous symmetry, this means for 4 dimensions and below, ordering is destroyed. In fact, the Emery-Ma phenomenon has been proven rigorously for the random field Ising model, random field XY model, and their quantum analogs.
Sorry, what kind of disorder do you mean? Just any?
You mean?
Well, we have disorder in superfluids in 2D, in 3D, no problem.
Yes, but usually disorder decreases the transition temperature, I would assume.
No, it changes the transition temperature, but transition temperature is still there.
Yeah, but that if you go to infinite disorder, can you move more and more?
What do you mean by infinite disorder?
Arbitrarily large disorder. I grab a hammer and break it.
I think the Emery-Ma works for a kind of disorder that locally breaks the symmetry.
Yes.
So
A random field disorder.
It's a specific kind of disorder.
Exactly. True.
Any kind
So
of
just not any disorder.
No.
This is a specific
Exactly.
one.
But as far as I know, even if I don't care about Emery-Ma, so I go to higher dimensions, for example, there is still a critical disorder strength beyond which there is no ordering anymore. And as far as I know, there's no model that circumvents this aspect. But so basically, if I were to plot the phase diagram, where the x-axis is the disorder strength, while the y-axis is the temperature, then what the phase diagram qualitatively looks like for these models would be something like this. Sure, maybe at weak disorder, you have some transition temperature, but as you increase the disorder strength, ultimately the ordering disappears. And the question I want to answer, is there a model where it can exhibit something like this? Now, of course, you have to consider specific types of disorder. You can't just add everything. But even when you consider specific types of disorder, is there a model that has a transition temperature that is asymptotically non-zero in the infinite disorder limit? That's what I'm trying to consider. Okay. Now, if you have a counterexample in mind that already exists, please let me know, because I'm not sure if there exists.
What do you mean by counterexample?
Oh, so this is for all models that I know of, in any dimension, they follow this curve.
An example along your lines, you mean? Counterexample to this?
Yes.
Because that's what you are going to do.
Yes, exactly, of course. Yeah, so for the Emery-Ma example, H critical would be 0, in low dimensions. Okay. So in this talk, I'm going to construct these examples, these red line bilayer systems. And the question is, okay, I can construct them, but are they relevant to physics? Are they natural in any sense? And I want to argue that they exist in bilayer superconductors. In fact, they probably exist in 2-component superconductors in general. Recently, there has been experimental evidence in time reversal symmetry breaking when 2 layers of bisco are rotated at some critical angle, 45 degrees to be exact. And in a previous work with my advisor, Steve, we showed that disorder can induce such a disorder, induce a time reversal symmetry breaking behavior. Now, in our previous work, we only studied the weak disorder regime, but as I will show you, the strong disorder regime has a much richer phenomenon. Okay, so now the explicit model. So the Hamiltonian is classical, and it's going to be given by this. The first term basically is an XY model for each layer, top and bottom. Theta plus and theta minus are the xy spins. And I have normalized the in-plane coupling strings to 1. So 1 is my energy scale here. For my disorder term, it's basically an interlayer interaction that only depends on the phase difference of the two layers. Alpha is going to be the random phase given by disorder that is uncorrelated from site to site and can be 0 or pi on each site. And then, of course, H is going to be my disorder strength. Now, because of how the disorder is only coupled to the phase difference, it's more convenient to rewrite the 2 degrees of freedom into the average phase and the phase difference. Now, of course, if I were to take these change of variables literally, then my definition is not 2 pi invariant, right? If I change my theta plus by 2 pi and theta minus, I keep it the same, then my average phase changes by pi. So, this is not correct.
Sorry, can I stop you? So you were talking about the twist at 45 degrees.
Yes.
So in that case, shouldn't it be 2 phi over there?
2 phi. Oh, yes. That's what Marcel Franz proposed. So basically, what Marcel Franz was that he didn't have disorder in the system, so no alpha, and what he had in his interaction was cosine 2 phi. That was how he generated time reversal symmetry breaking. But I'm saying, okay, so sure, he could do that, that's fine. But first of all, in order to generate time reversal symmetry breaking, he had to choose the sign of his order parameter, or his coupling, to be positive. So if he had a cosine 2 phi term, in order to generate time reversal symmetry breaking, the coupling has to be positive. It can't be negative. Now that's a problem. Why should it be positive? There's no reason. I mean,
it is naturally positive.
Yes, he did some microscopic.
I have to make a remark. The Tineco sign, actually, I have a paper much before him. But anyway, so your model now is actually a different philosophy. What you are saying,
Yes.
that you have a different mechanism.
Yes.
And then the 45 degrees is not essential in some sense in your thing, because then it's just any just coupled 2D superconductor.
So the reason that we thought about this order is because the reason that they considered cosine 2 phi is because at 45 degrees, cosine phi disappears.
Yep.
Right. So, but that only disappears on average. You could have disorder where on some sites it's plus cosine phi, and on other sites minus cosine phi. And I'm considering this type of interaction.
Excuse me, out of curiosity, is there some fundamental reason why you want to keep alpha under the cosine, given that it's 0 and pi? Maybe you can just remove alpha and allow H to be positive and negative.
Oh, it's just easier once I introduce how the intuition behind the proof. Yes.
Somehow your disorder is not generic. Yeah, I understand that, well, if you introduce disorder which doesn't touch some of the variables, take it to infinity, who cares?
Sure, that's always possible.
But do you have also disorder for theta plus plus theta minus? Or
No.
there's no disorder for the sum?
No. The reason, yes.
No, I'm not asking about the reason. It's a
No.
model.
Yes, there is no disorder on
So
theta
which
plus.
means in the channel which is the sum of two phases, there is no disorder whatsoever.
Yes, yes.
And this order probably will survive because...
Sure, perfect. Exactly. But do you expect the order phi to survive? The transition?
So you say, well, the order will survive in the difference as well.
Yes, exactly. Yeah. Ultimately, the reason that this ordering, the ordering of phi survives is because the average phase survives. They are strongly locked together, that no matter how much disorder you add into it, they won't be decoupled. Okay? Any more questions before I move on? Yes, so the point is, what I was saying was that, okay, you have this change of variables, but this is not well defined in a 2 pi invariant manner. Now, for this talk, I will ignore this problem, but in the paper, I treat it fully in the full 2 pi invariant manner. It's less apparent and intuitive based on the change of variables. So, in this talk, I will ignore the subtlety, rewrite my Hamiltonian as in these two variables, and we get something like this. Okay. Oh yes. Okay, so even though this model is inspired by bilayer systems, there's no reason that it's restricted to 2 dimensions. It can be defined in any dimensions on any graph, right? the gradients are going to define the edges, and the phase difference is just the on-site intercomponent coupling. Right? You can think of this model as a 2-component superconductor with intercomponent disorder for some reason. Okay, so for the majority of this talk, I'm going to focus on 3 dimensions and above, while I'm going to talk about 2D systems separately. Okay, so first, I'm going to look at the 0 temperature ground states. So since alpha is 0 pi, the interaction is just plus or minus cofine. What this means is that the system has a Z2 degeneracy based on this reflection, phi to minus phi. And so the usual U1 symmetry of the phase difference is broken down into Z2, and that means I'm going to be looking for Z2 degenerate ground state. So 2 degenerate ground state. Okay. Okay, so because we're at 0 temperature, this is the regime that we're going to be focusing on. Okay, so because the disorder strength is very large, the ground state has to first and foremost minimize the disorder state. That means the phase difference has to be really close to the random phase at each lattice site. So I'm going to assume that my deviations are small relative to the 1 energy scale that I previously talked about. Okay, based on this assumption, I can see that the disorder term is just quadratic to lowest orders. Okay, now I'm going to do the same thing for the first term. I'm going to assume that the average phase is long-range ordered. Now you can argue with me that this is not true, but in my next section of my talk of finite temperatures, I'm going to prove to you that this is actually true. It's just that it's easier to make this assumption now and see the ground states than giving you a full proof first. So basically what I'm saying is that in the next section, I'm not going to assume this anymore. Okay, so even when the theta is long-range ordered, I can use delta phi as my small parameter, expand the first term in Taylor series, and I only keep linear orders, because any order higher than linear is going to be, dominated by my disorder because h is very large. Okay, I have a linear order here, I have a quadratic order here, I complete the squares. So now it's just some quadratic Hamiltonian. Okay, so now of course I'm neglecting higher orders. So, based on this quadratic Hamiltonian, it's clear that the ground state solution is just the linear part. Okay, so first notice that it is on the scale of 1 over h. So in the strong disorder regime, this means that delta phi is small. So our assumption is at least self-consistent. Now let's see what the ground states actually look like. So the left diagram is going to be a real space plot. The green clusters are basically sites with random phase 0, so plus cosine phi interaction. And the red sites are going to be alpha being pi, so minus cosine phi interaction. And then I'm going to plot the right diagram. I'm going to plot what the phase difference looks like in spin space, so e to the alpha. Okay, so deep within my green cluster, all its nearest neighbors have the same random phase, which means that this gradient term has to be 0. So delta phi is 0. So my phase difference is perfectly aligned along the random phase, so the green arrow. Similarly, if I'm in my red regime, delta phi is 0, and it's perfectly aligned along the red arrow. However, things are different along the boundary. Because there is a non-zero gradient of my random phase alpha, my delta phi is going to be non-trivial at the boundaries. In particular, you can do the calculation and find that delta phi is positive, which means this dashed green arrow. There's a slight slanting in the upwards direction. You can do the same thing for the red boundary and find that delta phi is negative, which means a slight slanting in this direction. So overall, there's a net slanting in the plus pi over 2 direction. And that means the Z2 symmetry is broken, right? The overall net phi is in plus pi over 2, and that breaks the phi to minus phi degeneracy. And also from this consideration, we see that ordering lives only on boundaries of these clusters.
Excuse me, can I ask a very nice question?
Sure.
If your disorder is non-correlated, the notion of cluster is purely microscopic. So you are talking of some boundaries, but those are just some microscopic details.
Right.
Why do you need to invoke them? Because if you, upon coarse graining, we should, in my opinion, correct me if I'm wrong, we should just forget about those boundaries and discuss something coarse grained.
So, as I will show, the importance of these clusters are going to be because they percolate. So no matter how you coarse grain it, you can't coarse grain out a percolating cluster. The point is that even though alpha are uncorrelated from site to site, the ground state solution depends on this gradient. So there is an edge defined, and that means it defines a boundary. Does that make sense? So,
Frankly, it's hard to me to get the idea of percolation of the clusters, because if it's just 0 or pi, and they are absolutely random.
yes.
Percolating cluster would remind me of, of the icing transition when you have large clusters, blah, blah, blah. But if we are in the high temperature phase, that's my assumption, there should be no percolating clusters.
Yes. So even though the disorder is uncorrelated, there's an emergent percolation process here.
That's what I do not understand.
Yes,
Okay,
the
maybe
emergent process comes from the XY model, the nearest neighbor coupling of the XY model. Somehow, even though the random phases are uncorrelated, because there is nearest neighbor coupling, a site percolation problem emerges. So it's not apparent, but at least from the ground state solution, you can tell that it does depend on the gradients. Any more questions?
But the alpha is not.
Yes, it's
coupled
perfectly
to-
uncorrelated from site to site. But when you calculate the order parameters, such as delta phi, it cares about the gradients of alpha. Okay. In any case, I will talk about this in a bit once we go to finite temperature.
So excuse me, just follow up. My point is that apparently, apart from the definition which you gave, alpha equals 0 or pi, there should be something hidden
Yes.
which stands behind your notion of the cluster.
Yes.
Because if it's an exhaustive definition of the cluster, all clusters are supposed to be microscopic.
So I'm using cluster in the mathematical definition. 2 points are connected if there are edges of your underlying graph that can make a path. So that's what I mean by cluster. Okay. I'll talk about this more in detail in the finite temperature.
Sorry, can I ask you, so alpha is for you a continuous variable between alpha and
No,
pi?
0 or pi.
Okay, because then I'm a bit confused. So if you define a gradient, wouldn't be always like pi?
Discrete gradient, just
Exactly, but then it's always pi, no?
or 0, right?
Or 0.
Yeah. So if it's 0, nothing happens. Sine 0 is
Okay,
0.
otherwise it's 1. And then
Yes, exactly. So at the boundary, there's something different. In the depths, nothing happens. Good questions, all good questions. Okay. Okay, so of course that's what the ground state looks like in the change of variables. But what does it look like in the original variables? The purple arrow and orange arrow corresponds to the top layer and bottom layer. And so this is what the ground state looks like in the original spin. You can see that in each cluster, deep within each cluster, they are collinear. So in the same direction or in opposite direction. But at the boundaries, they are slightly different. Also notice that the relative orientation between the two clusters are at a plus pi over 2 direction. So that's kind of interesting. Okay, hopefully that makes sense. Now let's talk about why it's an emergent fractal. Okay, so like I said, the ordering only lives on boundaries. The slanting only lives on boundaries. So if I took that literally, and I were to calculate something like the average magnetization, where sine is going to tell us whether the slanting is upwards, nothing, or downwards, then what this average magnetization should give us would be a boundary over volume contribution, right? Because the slanting only occurs on boundaries. Okay, so if you took this literally, then what this means is that it should be a 1 over L contribution, and in the thermodynamic limit, it disappears. But I'm claiming it doesn't disappear. The reason behind that is you have to go back to the 80s or 90s and find that the lengths of these boundaries are actually proportional to the volume of these clusters. And so it is fractal-like. And so the average magnetization doesn't disappear. Okay. So the name Emergent Fractal. Okay, so that's the zero temperature ground state. Now, generally speaking, we know that the critical transition temperature is usually on the same scale as the zero temperature order parameter. This is especially true in superconductors where you have a well-defined gap. Now, in this case, what our ground state analysis tells us is that the slanting is on the scale of 1 over h. So, okay, sure, there's a non-trivial ground state, but maybe the transition temperature is asymptotically 0, right? So, okay, sure, there's some non-trivial ground state here, but maybe it doesn't survive up to finite temperatures, and then it would be much less interesting. So the next section is to convince you that that's not true. It's going to be asymptotically non-zero. Okay. Okay. So finite temperature. Let's look at the Hamiltonian. We are in the following regime: disorder much greater than in-plane coupling, much greater than temperature. Okay, we can do the same ansatz, right? My disorder is still very large, so I can assume delta phi is small, and then I have quadratic orderings. But now, I cannot assume that my thetas are long-range ordered anymore. But I can still expand the first term in power series of delta phi, and then I still only care about linear orders in delta phi. In this case, I can rewrite my Hamiltonian as follows. The first term depends only on the average phase, while the second term depends on both delta phi and the average phase theta. And then I'm neglecting higher order terms. Okay. What this tells you is that if I were to fix the average phase, that the delta phi has a conditional probability that is Gaussian, right? It's just quadratic. It has some mean and some standard deviation. Now, what this fancy writing tells you is that if I were to calculate the thermal average of my order parameter delta phi with respect to my full Hamiltonian, it would be equivalent to replacing delta phi with its conditional mean and computing that thermal average with respect to my effective Hamiltonian. So what this tells you is that if the effective Hamiltonian has a non-zero transition temperature, then so does my delta phi. So far, so good? Okay. Okay, so in that case, I can look at my effective Hamiltonian. That only depends on the average phase. This actually comes back to the question sorry, what was your name again?
Hi.
Your name? Yes. You said, you talked about how the average phase is not coupled to the disorder.
Yeah, no, I understand.
Exactly.
Yeah, this transition will survive because nothing happens to it.
Exactly. But it's not apparent because the disorder is coupled.
Because you say one layer can order as conventional XY, the second one will simply minimize whatever is Josephson coupling between them without paying attention.
Well,
but the first order orders at TC, nothing can change it.
It's not the independent layers that order.
I understand, but in the limit you discussed, the second layer can adjust to the Josephson coupling.
Well, it's both
while
layers.
Keeping the first layer just completely ordered in one direction, don't pay any attention.
So the average phase orders, but not each independent layer. If you
Well,
were
let me present another state. Yours is probably even better. But mine is saying,
sure.
layer one, just order it completely
Yes.
in one direction. Forget about everything.
Sure.
You say, I have a pi difference with the second layer. So completely disorder the second.
Perfect.
And you minimize your energy perfectly well.
Yes, but the two
Because
layers
the
aren't
second
coupled.
layer takes care of disorder. The first layer simply orders in one direction at TC.
Sure.
So
But
TC is
if
fine.
they are uncoupled, of course that happens. But if they are coupled
No,
together,
they are coupled strongly by H.
sure, but H will ultimately surpass your in-plane coupling of your first layer, right?
No, I'm just saying, maybe you can do something even better. First layer doesn't even care about the second one. The second one takes care of H. completely. So the second layer can be completely disordered. But I understand that at TC I will order.
Maybe
Because I
we can talk about this in a
to-
second.
To a large degree, I minimized every single term in the Hamiltonian.
Sure. Maybe we can discuss this afterwards. Okay, so let's look at the effective Hamiltonian. So even without going into details, notice that my first order term, this term is first ordered in 1 over h. So in the large h limit, what determines the transition temperature is going to be the first two terms. Okay. So what is the zeroth order term? So first, I'm going to go back to my cluster model, partition again, and the first term is literally the XY model on my subset. So as you can see, a cluster definition is then well defined because the XY model has nearest neighbor gradients, and it's only on sites with random phase 0. So the green cluster is truly well defined. And then of course you have the red cluster, which is the second term, alpha pi. Now because at the zeroth order level, the two terms are perfectly decoupled, I only have to consider one of them when determining the transition temperature. Okay, so theta plus, theta minus. So let's only care about the green cluster for now, and remember the following. Alpha is 0 with probability 1/2. If this 1/2 probability is larger than my site percolation threshold of my underlying graph, so if this was 3 dimensions, then my graph would be Z3, then the green cluster is going to be infinite. There's going to be a unique, infinitely large green cluster. And so that means there's a well-defined thermodynamic limit. And so the XY model on my green cluster is going to exhibit a finite transition temperature. Now to prove this rigorously is quite tricky, but ultimately that's the intuition behind it. And in 3 dimensions, this inequality is indeed true. Okay, so indeed there's a percolation problem that's hidden behind this disorder model. Okay, so with that understanding, I can now assume that basically each cluster is long-range ordered at low enough temperatures. So what about the relative orientation between the two clusters? Well, that's where the first order term comes in. What this first order term really tells you is that it only cares about the change in the average phase across different clusters. So basically, this R equals boundaries. That's what I'm trying to tell you. So that means it only couples to the relative orientation. Now, of course, this interaction is a bit complicated. So let me try to simplify it. I'm going to rewrite this interaction as a cosine square phi term. It has the same symmetries as the original interaction, but it's just visually simpler. And then, of course, you have the XY models on each cluster. So basically, what I'm trying to convince you is that after some rigorous proof and technical details, this effective Hamiltonian can be reduced to a bilayer clean Hamiltonian with a cosine square phi interaction. And notice that we went from a strongly disordered model to a weakly interacting bilayer system. Any questions? So this is the simplified model that you should have in mind. Okay, so in that case, it's quite easy to see that the ground state solution of this interaction is just relative orientation 0 or relative orientation pi. If the relative orientation is 0, so that all the thetas are aligned, then I have my ground state slanting upwards. If I have phi equals pi, then my ground state is slanting downwards. Okay? Okay. So, just to reiterate, what I have done is that I've started out with a full bilayer Hamiltonian, and using the ansatz that delta phi is really, really small, I have gotten this effective Hamiltonian. And the question is, okay, this ansatz is nice and all, but is it actually true? Can I actually use the effective Hamiltonian to approximate my full bilayer Hamiltonian? And so here we give you some numerics in 3 dimensions. So the x-axis is the disorder strength in exponential scale, so 2 to 0, 2 to 1, blah, blah, blah. And then a y-axis is the temperature. The red is going to be the transition temperature of my full bilayer Hamiltonian, while the blue is the transition temperature of my effective Hamiltonian. And as you can see, the two coincide at large disorder. Now, 2 to the 5 is the largest I can simulate. Maybe you can do more if you want. Okay, so 2D system. So why didn't I care about 2D systems in this talk? Well, of course, there's the BKT. But another reason is because I needed my green and red clusters to percolate.
Excuse me,
yes.
a question. If your broken disorder is Z2, what BKT we are talking about?
Oh, the BKT of each cluster has the average phase is quasi-long range order. So the phase difference is Z2, but there's also an average phase that is still U1.
Are you saying that in your model you still break U1?
Yes, so it's U1 times Z2.
Okay.
And they probably break together,
Okay.
but I have no proof. Okay, so yes, so there was the BKT problem, but there's also a second problem. The second problem is that I needed the critical percolation threshold of my underlying graph to be less than 1/2. Now, however, on Z2, that's not true. You have the converse. In fact, on any planar graph, this is not true. So my argument kind of breaks down. So does that mean in 2 dimensions we have nothing? Well, that's only if we have planar graphs in the mathematical sense. If we have non-planar graphs, that is not true anymore. So for example, a non-planar graph would be the usual Z2, so its nearest neighbor couplings, plus next nearest couplings. So that would make the graph non-planar, and so I have my inequality is satisfied. Okay, so I can go through the same proof, and as you said, the problem here is that each cluster is not long-range ordered anymore. Each cluster can only be quasi-long-range ordered. And so, at best, my relative orientation of the 2 clusters is at least quasi-long-range ordered. But can it be better? Can it be long-range ordered? So basically what I'm saying is that it is infinitely quasi-stable in 2 dimensions because of the quasi-long. Okay, can 2D systems be infinitely stable? So that's a good question that I don't have an actual answer to, but I will try to convince you the following conjecture. So remember that my, under some proof or whatever, my effective Hamiltonian was reduced down to this clean Hamiltonian, where you should think of now the clean Hamiltonian of 2 bilayers, and this is the interlayer weak interaction. Now this system has been studied quite well, just like Marcel France has studied it. But there are also a lot more literature on this StatMech model. Right, the cosine square is just a cosine 2 in disguise. So people have done calculations, either it's RG or numerics or mathematics. Basically what they seem to see is only one single phase transition from a high temperature phase to a low temperature phase. And it seems that it is immediately long range ordered after this transition. But there's no proof. So if we were to believe that it is immediately long range ordered at some transition temperature, at the scale of 1, then the magnetization or your order parameter should follow this curve, just from conventional wisdom and universality and all that stuff. Okay, that's good. But in our paper, we can actually prove rigorously that the magnetization has to be upper bounded by this exponential decay. So what this means is that if my disorder strength, H, or this coupling is really, really weak, then my magnetization has to be upper bounded by this red line. I can take this 1 over log H scale to be smaller and smaller and smaller, and so that somehow this red line is below this black curve. And so we seem to have reached a contradiction. And so that means it's probably not true that long-range order occurs at the scale of 1 anymore.
So I missed, why there's long-range order in 2D?
Oh, because of previous, people have previously studied this clean Hamiltonian. So each XY model is on a 2D system, and then there's weak interlayer interaction. So this system people have studied relatively well. There's a lot
Phi
of...
is phi plus minus phi minus?
Yes, it's
the difference.
It's a difference. Yes.
But then then it's like one layer.
Well, it's 2 layers, right? It's, there's theta plus and theta minus again. So I'm
Right, so it locks, doesn't phi lock the 2 layers together?
yeah.
And
So
then-
you would think the
so
long
then it's
range.
an XY, it should be no long-range order. In the
But it's a D2 degeneracy, so it's a discrete degeneracy, right?
Z2 long range order, right?
Yes, yes.
Oh, Z2 long-range order, but the total phase, phi plus phi minus is quasi-long-range order.
Yes, that's I think what they see in numerics.
Right,
So
okay.
so that's what I'm trying to say.
It's
So-
just they lock together in the Z2.
yes.
Okay,
So
in the Ising way, okay.
so they claim that there's long range order at transition temperature 1. So basically, it doesn't depend on how weak this is. It could be arbitrarily weak, and numerics and RG tell you that the transition temperature is like 1. On this, it doesn't care about scale. But if that was true, then you would think that the order parameter follows a curve like the black line. Okay, so suppose that is true, it follows this black curve. But then I'm telling you that I can prove rigorously that the magnetization is upper bounded by this exponential decay. And this exponential decay depends on my interaction strength. So then I can just push my interaction strength basically to 0, and so that this red line is below this black curve. Now, this isn't a rigorous proof, right? There's no reason that it has to follow this curve. It's just I'm saying that conventional wisdom tells you that the order parameter should be substantial once it's below the transition temperature. And so it's not a full proof. Only this upper bound is a full proof. But I think it's relatively convincing evidence that you cannot have a transition temperature on the scale of 1. Okay, so basically what I'm saying is that the conjecture is that there is long-range order at the transition temperature on the scale of 1 over log h, while quasi-long-range order sets in at the scale of 1. And then what this means is that there seems to be an intermediate massless phase, despite having a Z2 symmetry in my phase difference. And then, then why do I not see this in numerics? Well, it's probably because of the logarithmic decay. It's really slow, so you're not going to see it in numerics. And maybe it's not even relevant for experiments. But from an academic standpoint, I now think that the long-range order occurs at 1 over log h scale. Okay, so just a summary of my results. In 3 dimensions and above, I prove that the long-range order occurs on the scale of 1 because of site percolation. On planar 2D graph, this is probably not true anymore because there is no percolation. And then non-planar 2D graph, I have quasi-long-range ordered on the scale of 1 because of percolation, EKT. And then finally, this is a conjecture, not a proof anymore. I conjecture that long-range order occurs on 1 over log h scale because of the upper bound. Okay, that's it.
Thank you.